Okay, welcome back to 240. Just a quick announcement about the schedule. A lot of you have pointed out to me that the Telebear schedule changed the class to 11 o'clock. As far as I know, it's still 9:30, so just show up at 9:30, and I think we're all set with the schedule. Um, any other questions or comments before we start today's lecture? Okay, so let's start. Today we're going to talk about, spend a lot of time talking about CMOS technology, kind of do an overview of that, look at the process cross-section, and then we're going to focus in on the passive devices that are available to us in a typical CMOS process. And this is something that you probably don't spend that much time doing until you really take analog design seriously, because analog design needs very good passive devices, good capacitors, good resistors, and in some cases good inductors. So we'll go over the availability of these devices in a typical process. Okay, and I think we touched upon this last lecture. Why are we looking at this again? Well, it's a question of perspective. So we want to, hopefully by the next couple of lectures, give you the insight from an analog design perspective on the process and on the modeling. So we'll talk about modeling a lot more in next lecture. But today's lecture, just even on the process, you want to know what's important, what are the important considerations for analog design. Okay, so the process that we have available to us is the 0.18 process. It's a single poly 6 metal level process. It's a fictional process. There's an issue with having, as I discussed last lectures, access to a real process. But we really have the next best thing here. On the Moses website, there's process data, run-to-run process data for a 0.18 process from TSMC. And what Professor Peter Kingett has done is he's put together a fictional model that tracks the variations in that process. So it should be pretty accurate in the sense that it represents a true analog process that you may use. But of course, it's a fictional process, so don't expect that you can just take your design and port it over to TSMC 0.18 and start making money. Supply voltage is 1.8 volts, which is somewhat of an issue. We'll see how it goes in this class. As the supply voltage gets lower and lower, it gets a lot harder to cascode stages, to get high gain, and you have to start playing other tricks to really improve the gain of op amps. And that's part of this course. That's what we're going to teach you guys. So why 0.18? Why not just go into a 90 nanometer process, which is available commercially today, or even 65 nanometer process? And then for that matter, why not bipolar or silicon germanium, or SOI or FinFETs, right? So that there's a good balance between something that's realistic, that is useful, and then something that would just be a pain in the butt. So if we use a 90 nanometer process, you'd have to deal with all sorts of issues like leakage that would be good for like a pure design course, let's say a 290 course, but probably not appropriate in this class. And some of the students who are in 142 can attest to this. Using a new process technology, a transistor doesn't look much like a transistor, and so you spend a lot of time wrestling with the transistor rather than actually doing good design. Well, why not bipolar or silicon germanium? I'll turn that around and ask you guys, why is it that we're going to focus on CMOS in this class? Price, yeah, that's actually a good reason, but why is it that CMOS is low cost? In fact, I could come back and argue that, well, CMOS technology is cheap if you're using it for digital, but if you put a couple of mask options and try to use it in an analog application, it's probably comparable to silicon germanium. So why is it that CMOS is still seen as such a popular alternative? Yes, in the back.
Is it full integration?
That's right. That's one reason. So for many years there was a drive for kind of single chip or system on a chip, SoC, And so people really wanted to put all the functionality on one die, and so you have a chip that has your microprocessor, it has your interface, it has your analog, it has your RF. The trends have actually changed a little bit. Let's say 10 years ago, the best digital process was more expensive than, let's say, one generation back. But you knew that because of digital scaling, because of the fact that the whole industry was using that process, within a couple of generations, the cost would come down significantly. And so even though there was a small barrier to going into a new fine-line digital CMOS advanced process, you knew that that was just a temporary thing. You'd pay for the mask once, and then you'd sell gazillion of these things, and it would be very, very cheap. And if you continued to modify that design in a new process, that same process, it would be cheaper and cheaper on each iteration. Why has that changed? Or why should we reconsider that strategy? Okay, I know some of you guys in here have actually worked in industry, so you have some good insights into this. Yes?
The initial barrier too high these days was nanometer.
Yeah, that's part of it. So how much does it cost actually to fabricate a CMOS 90 nanometer chip? How much do you have to pay for the masks? It's about $1 million, right? Give or take. It's a lot of money. So, 10, 15 years ago, it might have been $20,000, $30,000. Today, it's $1 million. So you really have to have a lot of money to do a chip, and you have to have a lot of confidence that your chip is going to work, because if it comes back and it doesn't work, you just lost $1 million. So cost is an issue. What are some other reasons why we might not want to go after system on a chip? Anybody? Christian? Any ideas?
Maybe sometimes you can get better performance by keeping things separate to reduce crosstalk.
Exactly, yeah. So there's a real divergence between what the process can do and what a previous generation can do. And I guess it's not a really good wording. Let me try to say that in a different way. So if you look at 90 nanometer technology, right, it has a 1 volt supply. So let's say you want to build a driver or power amplifier in this technology. Well, it's pretty hard to do that with 1 volt, right? It makes a lot more sense to use a technology that has 3 volt supply or 5 volt supply, so you can get much higher power output. So if you're going to use 90 nanometer, you're going to pay with performance. So we've gotten to the point where analog performance and RF performance can't really keep up with the technology scaling. For some time, technology scaling benefited both analog and digital, but we get to the point where today, as we scale technology, it actually gets harder and harder for analog to keep up with performance, at least traditional analog. Hopefully you guys are going to go out and change that, right? You're going to come up with new architectures that enable using 65, 45, and still get good performance. But if you use traditional analog techniques, what people do in industry, then you're basically going to pay a big price in performance. So then the idea of having one process for your digital and another process for your analog makes a lot of sense. And people call that system in a package, or multi-chip modules. So you would have one chip that would be your digital, another chip that's your analog, and you'd pack them together in one package very closely as if it's a single system, but now it's the system in the package. Okay. So if you talk to a lot of good analog designers, they would probably argue that 0.18 was probably the optimal point. After that, things just went bad, so to speak. Maybe even quarter micron. Okay, so that's a big reason why there's this divergence, and we basically maybe don't want to scale with technology if we have the choice. A lot of times we don't have the choice. You just have to take what you're given. Someone tells you, look, you're going to design an A to D converter in 65 nanometer. I don't care about your problems. You make it work, right? That's what I paid you for. So we also have to know how to do things in those technologies. Let's focus a little bit on silicon germanium, because that's a very popular process these days. Why is it that people don't do analog chips in silicon germanium? Well, in fact, they do. But why is it that we're going to focus on CMOS? Anybody? Well, there's some subtle reasons. Cost is always something that you can bring up, but it's not the full story. It's definitely not the full story. I think another reason that CMOS is so much loved, one is just availability. So if you're a fabless design house, meaning you don't have your own fabrication capability, you rely on somebody like TSMC or UMC or IBM to do your process for you, then there's certainly a lot more availability of CMOS. Almost everybody has CMOS, right? And now with new markets emerging like China, there are basically a lot of players out there that can give you CMOS. And so if you have multiple sources, it's a good thing for several reasons, right? One is if one source gets cut off, you can hopefully switch to another source. And two, you can basically bring the price down. So if you want the best silicon germanium process, you probably have to go to Jazz or IBM. And you don't have that much negotiating power because there's just not that many other players that can give you that performance. But if you're talking about CMOS, you can negotiate. So that's another reason why CMOS ends up being preferred. Another subtle thing to bring up here is portability. CMOS processes tend to be pretty portable these days. So if I design in one flavor of 0.18, it doesn't take me that much work to port my design to another flavor. In fact, a lot of times you can just tape the chip out again and get very comparable performance. So that's really nice. That's a very, very good thing, having something that's portable. Okay. Questions or comments about choice of technology? It's something that we'll discuss probably more as we go through the course, as we compare performance of different technologies. I guess just an important takeaway point on the slide is that there's business reasons for doing things and then there's technical reasons. And you really have to take both into consideration as a good engineer. Technical reasons, you would go for the best process. You'd go for a silicon germanium process with an Fmax of 400 gigahertz, and you get really good performance and low power. But you might not get the market. You might end up basically selling only a few copies of your chip. All right, so we talked about the supply voltage already, but here's just a graphical illustration of what's happened to the supply voltage. So for many years, the supply voltage was constant around 5 volts. And right around half micron, it just became infeasible to keep the supply voltage at 5 volts. And actually undesirable as well. So why was it infeasible and undesirable to keep the supply voltage high? I think most of you know it's the short channel effects. So supply voltage translates into field strength inside the transistor, and high fields are bad, right? Because high fields put stress on the device, they cause leakage, tunneling, they cause short channel effects, velocity saturation, hot electrons, right? All the nasty things that we'll talk about in this and next lecture. So in order to keep the fields roughly constant, the supply voltage had to scale with the device dimensions. And the digital people love this, right? Why is it that digital people did not mind scaling voltages? Power, right? CV squared F power. So V squared, right, is the power dissipation of a static gate. Scale the voltage, you scale the power by the square of that. So that's great. Analog, though, really has suffered. Why is it that analog can't handle lower supply voltages? Yes, Christian.
You need the headroom to do cascoding and things you were talking about before.
Sure, you need headroom, but why do you need headroom?
The more devices you start stacking up in a cascode, the less headroom you have and the lower swing that you can have at the output.
Okay, so swing. So why do we need swing? More fundamentally.
Gain?
Okay, well, no. How about?
Your noise floor remains pretty close to constant, so if you lose your swing, you're cutting down your SNR.
That's right. So it's signal-to-noise ratio. So if your signal-noise ratio is constant and you're losing swing, pretty soon your dynamic range is going to hell, right? And we'll talk a lot more about that in this class. So if that doesn't make full sense to you, it will in a couple of lectures. But everything you said was valid. Lower voltages, we get lower gain, we have lower swing available to us. But ultimately, it's dynamic range that we really care about. Okay. All right, so this is familiar to all you guys. This is a vanilla cross-section cartoon diagram of a CMOS process. In a traditional, I'll just make one note here. In a traditional CMOS process, your end FETs are actually in the substrate, right? And so their body contacts are all necessarily grounded. And so if you have any end FETs that are not basically source at ground, you have body effect. So just remember that when you're doing design in a what we call a single well process. Okay. On the other hand, your PFETs, you have the option. You can tie the body voltage really anywhere you like, as long as you keep the well junction reverse biased. And so typically you would tie it to the highest voltage available. But you can also just tie it to the source of the device and eliminate the body effect. Okay. So here's some typical numbers. Actually, this is from Professor Bozer's slide. I forgot to update this. So the numbers have obviously changed. This is for a 0.35 micron process. Now, of course, in this class, it's going to be 0.18. The junctions, as you'll notice here, the junctions have gotten very thin, even thinner than this in our process. And that actually is not necessarily good for the transistor. Why is it that thin junctions are used? And two, why is that bad for us?
Less short channel effect using thin junctions, and it's bad because of increased series resistance.
Exactly, yeah, right on the money. So we make the junctions smaller and smaller so to reduce the amount of, let's say, drain control on the channel. But as a result, because the junction's thin, the resistance is high. And so you pay the price. So there is an optimum point. A typical substrate these days is about 700 microns thick. That's really just for mechanical stability. You can use thinner substrates. In fact, people sometimes thin it down all the way to tens of microns. If, for instance, in applications where they're trying to get heat out of the silicon. So if you have a ground plane at the bottom that's also a ground plane effectively for temperature, then the power dissipation of these transistors will be removed through the backside of the substrate. So the thinner we make the substrate, the lower the thermal resistance. There are other applications for thinning the substrate. One is to have flexible chips. If you make this thin enough, it's flexible, and then you can put it on contours that are not flat. Other applications are for taking one process and housing in another. So for instance, if I don't like this conductive substrate, then I could thin it away and then mount this onto another wafer that has a different resistivity, let's say a higher resistivity, where I could put passive devices that have better quality factors. Okay, so in a typical process, you have lots of flavors of NMOS and PMOS devices. In the old days, you may have had one or two. Nowadays, you have lots of options. Low VT, high VT, thick oxide, thin oxide, and every combination possible. Of course, in a silicon germanium by CMOS process, you'd also have bipolar or heterojunction transistors, NPNs, PNPs. But even in a traditional CMOS process, you have PNPs and NPNs. They're just parasitic devices, and they don't work very well. And you also have diodes. You might have a custom diode, or you may have, again, a parasitic diode that, again, doesn't have very good performance. And we'll talk a little bit why the performance is not good. Today, we're going to focus on the passive devices, resistors, capacitors, and inductors. Okay. So very quickly, let's talk a little bit about why in a traditional CMOS process you don't have good bipolar devices, right? So intuitively, it seems like you should, right? We go to the, can we switch? Okay, so if we look at a specialized process, right? Let's say this is our N, this is our P, this is our base contact, this is our emitter contact, and we have our subcollector here. This is N+, so this is again N. And so it's a vertical structure, and this is our collector. On the other hand, if we look at CMOS, traditional CMOS, let's say we wanted to do an NPN. Well, here's an N, here's an N, and here's the P, which is the substrate, right? Why isn't this a good transistor, right? So I could contact here. This could be like a P plus contact. Well, I could put it over here, let's say. I don't want to put it here because I want to make this channel length as small as possible. So this could be my emitter, this could be my collector, and this is my base. Why isn't this a good transistor?
Because of the alpha factors, because all the bases leaks to the substrate, so you won't get a good alpha factor.
That's right. So remember, when you inject carriers from the emitter into the base, what you want is you want to collect them all here at the collector. But in a real transistor, why should the carriers go to the collector when they can in fact go into this huge substrate, right, and get collected by ground? So only a small fraction of these will go to the collector unless you basically put the collector very, very close to the emitter. Now, you could argue that you could do that in a modern process. You can make these very close. So why is it that you still don't get a good transistor? Yes?
It's a surface device, lower mobility.
That's an issue, yeah, that's an issue. But even beyond that, there's basically a fundamental problem with doping, right? This is a symmetric transistor. The emitter and collector have the same doping. What we really want is we want to dope this optimally. You know, we won't go into the device physics, but you want to dope it optimally so that you're injecting more electrons than holes, reverse injection, and then you want to collect all those electrons. So it's not just the distances, you also have to really have the right doping profile. And there are other issues too. Well, how about if we do a PMOS device, because that has a well. So that seems like that could help, because at least the well could be reverse biased. So now the carriers from the emitter, this is a PNP, now at least our carriers, basically, if you look at this picture, you see that the situation's really no different, because now I can either have a PNP device in this direction, or I can have a PNP device in this direction. And certainly this is going to capture more carriers, holes in this case, than this little junction is, right? Even if I completely surround this junction, there's still much more area going vertically. So I end up getting a vertical substrate PNP rather than what I desired, which was a lateral PNP structure. Well, it's interesting. So this is the conventional way of thinking about it. But if you look at Journal of Solid State Circuit, you'll find that people have actually built decent PNPs and NPNs and traditional CMOS processes. And if I remember, I'll give you guys a link to that article. So it's true you're not going to get a great device, but you can actually get a pretty decent device. And for many applications, you end up with sufficient FT and sufficient gain that you can actually use it. So when you're using a traditional CMOS process, keep that in mind, that there are these devices that you could make that aren't really supported by the foundry. But if you have a little bit of time and you can characterize them, they actually might be decent. You might be able to use them. Okay? Questions? Comments? Okay, so let's start out with resistors. So in standard CMOS process, there really are no provisions for resistors. It's basically not supported. And by standard, I mean like digital CMOS. So you have to really design your own resistors. And what can you, basically a resistor is some kind of material that has some resistivity. So if you look at the typical materials that are available to you, and you characterize the resistance per ohms per square, because really you have no control over the thickness, right? You only have control over the length and the width. The thickness is set by the process. So if you're using a piece of aluminum, In a typical process, it's on the order of, let's say, 50 to 100 milliohms per square. So you can design some really small resistors, but probably that wasn't what you were looking for. You're looking for, let's say, a kilo ohm or 10 kilo ohms. So using just metal is really not a good idea. You'd have to make very, very thin resistors to try to get a large L over W. And basically, just to get 60 ohms, you need an L over W of 1,000, just to start off with, right? And to get to, let's say, 60 kilo ohms, right, it's just too big. It's not practical. Well, there are other layers available to us. There's the polysilicon itself. Polysilicon these days, if you look at a typical process, it's actually pretty low resistance. It's on the order of ohms per square, or 5 ohms per square. If you look back to like a 5 micron process or a 0.35 micron, that's like 50 ohms per square. So what's changed? Why is it the resistance is now lower? Lots of technology people here could give us the answer. Yes?
Silicide?
That's right. So most modern processes use silicides in the source and drain junctions, and as a consequence, the gate. And so the polysilicon resistance is actually much lower. And we'll talk about ways of blocking that to get a better resistor. It's actually a process option. You could also use a diffusion layers, right? You can make a diffusion resistor, about the same order of resistance, about 5 ohms per square. What's the disadvantage of using a diffusion resistor as opposed to a poly resistor?
Temperature variability.
Okay, temperature. What would you worry about probably more than temperature? All right, let's look at what a diffusion resistor looks like. So let's say I just make an N plus region and I put contacts on either side. Is this a resistor? Yeah, right, it's going to be a resistor. But it's also a distributed nonlinear capacitor, right? So these are all reverse bias junctions. It's reverse bias to give you isolation from the substrate, but because this is a diode, it looks like a nonlinear resistor. Why is it nonlinear? Because the depletion region width changes as we change this reverse bias, which effectively changes the thickness of this diffusion region. That's bad. We're going to try to use these resistors and operational amplifiers that have really good linearity, and if our resistor has a voltage coefficient on it, that's going to hurt us. Okay? But you're also right. There's temperature variation. There's also, more importantly, process variation. The resistivity will vary quite a bit for a diffusion resistor because it's not necessarily a very well-controlled parameter. As a process engineer, you just want to get the resistance low enough in the diffusion regions. You don't necessarily want to target a certain value. Okay. How about N-well resistors? Switch back to the laptop. You can see that also the nice thing is now, because the N-well is much more lightly doped, you get quite a bit of resistance, on the order of kilo ohms per square. So clearly this seems like the best way to build resistors, but it has the same problem. It has a voltage coefficient because it's a reverse bias junction. Okay. Now, if you're using a non-CMOS process, there may be special thin film resistors available to you, which are basically materials that are not used in the standard CMOS process, but you can also always add them in post-processing. And if it's a really specialized process, you might even have provisions for trimming those resistors, like a laser trim, to get a very precision value. Okay, but that's rare. Most of the time, if you're working for the military, you're going to have to live with these different layers. Okay, but it's very rare to actually build a chip in standard digital CMOS. What's much more common is to actually use some kind of process option. And there's several options that are available to you. the one that we're going to focus on is really the silicide stop, which lets us get higher resistivity out of the polysilicon. It's almost a necessity if you're going to do analog circuits, precision analog circuits. You have to have a decent resistor somewhere, and so the silicide stop is a very commonly used option. Other things that we'll talk about a little bit later are capacitor options. Many processes today let you have MIM capacitors, high density MIM capacitors. MIM is a metal insulator, metal capacitor, or two levels of poly where you can build a high density cap out of the poly. Low VT devices or zero VT devices are becoming pretty common because you can get good performance out of a low VT device, but it's too leaky for digital applications. So you want to have the option of putting the low VT where you need the performance, but the high VT where you want good power dissipation in standby mode. High voltage devices are universal. Always there's a thick oxide device to allow you to drive off-chip signals. For instance, a 3.3 volt device for driving a legacy CMOS process, or in analog applications for driving, let's say, a small load with lots of power, or a power amplifier, or let's say a DSL modem. Lots of applications where you actually need to drive resistive loads and you want to put substantial power into those resistive nodes. Okay, so for those of you who aren't in process, just a quick slide on what silicide technology is. As we mentioned, it's an implant to lower the resistance of the drain and source, and the way it's done is basically it's also beneficial to lower the resistance of the polysilicon for the transistor, right? Because that's your gate resistance, and you want it as low as possible. So it's, in a normal process, it basically goes everywhere, and different materials are used. For instance, titanium is common, cobalt, platinum. The point, though, is that what we really want to do is we want to get rid of silicide selectively. So we want to have it on top of our transistors, but we want to block it for our resistor so that we can get higher resistance. Okay, and so here you can see what happens once you block that silicide. You can see right away that all the resistances go up. So our poly, which was like 5-6 ohms per square, is now 100 ohms, 200 ohms per square. And the same thing for our diffusions and end wells. They all go up. So the other point that was already brought up was, one is the temperature coefficient. So these resistors have different kinds of temperature coefficients, and the terminology, which is very common, is parts per million per degree C. So how much does the resistance change parts per million? So parts per million just means multiplied by 10 to the minus 6 per degree C. And then a voltage coefficient, again specified in parts per million per voltage. Okay. The voltage variation is a little bit more difficult to talk about, because a resistor, what voltage are you talking about, right? There's two voltages, there's one at one end, one at another, then there's a whole series of voltages inside. So we'll talk a little bit about the notation for the voltage coefficient. Well, you'll notice here that the temperature coefficients for these polys are actually have different signs. And what are we going to do about that? Is that a problem? Yes.
Can you use them to cancel each other out?
Yeah, that's right. That's actually a nice feature. In fact, whoever designed this process probably did this on purpose. The nice thing is that, I'll do an example here. Let's say we want to design a 100 kilo ohm resistor, and to first order, we like the temperature variation to be 0. In other words, change in resistance over temperature should be equal to 0. Well, you can do that if you use two different materials that have exactly the opposite temperature coefficient. Unfortunately, their magnitudes aren't the same, but that's okay. We don't split the resistance equally. We split the resistance so that the overall temperature coefficient cancels out. So here, I'm going to design my resistor with N poly and P poly, and this is the variation, right? These are the two coefficients which we want to cancel out. So if I just write this out, this is the total resistance, and then for the temperature dependence to go away, this part should be equal to 0. And so you can solve, since these two are known, you can then solve two equations, two unknowns. This is the total resistance, and this should equal to 0. So in this particular example, it's trivial. You can see that 20K should come from the N poly, and 80K should come from the P poly, and then translate that in based on however you lay it out, 200 squares and about 400 squares. Okay. Any questions about that?
Previous slides, what is a B anyway? BC.
We'll talk about that a little bit later. Yeah. Okay. Questions about this slide? Okay. So coming to your question. So as we've discussed already, all these resistors that are actually physically in the substrate are basically junctions, right? And the depletion region width is a function of the reverse bias, which changes the thickness of the material, so you end up getting a voltage coefficient. And this is one way to describe the variation in resistance. You can see that it's a linearized model, right? Clearly that this is a simplification, but for small changes it should be pretty good. It's just like doing a Taylor series expansion. So you can see that the resistance changes based on the difference in voltage and the average voltage, right? So the average voltage would be kind of this voltage plus this voltage divided by 2, assuming that the voltage variation here is linear, probably a pretty good assumption. And the difference voltage is really the fact that, you know, over here if you have a really high voltage and here really a low voltage, the depletion region widths will be different, so it's not a uniform thing. If you were to somehow even put roughly the same voltage across here and just apply a small differential voltage, you would still see a variation in resistance. And so this is captured here by these two sort of moments, the average moment and a difference moment. If we go back and look at some of the numbers, you'll see that even the poly resistors have a VC coefficient and a BC coefficient. Why is that? Yeah, poly depletion. So even though our polysilicon resistors are not physically touching the substrate, so they don't necessarily get reverse bias like a PN junction, they still will get depleted, and so you actually get so in a transistor, I'll draw a real quick cross section. If you build a transistor like this, you find that the actual oxide thickness, if you measure the CV curve, is not Tox, but a little bit higher. And that's because the carriers are actually depleted and don't flow all the way to the edge here. And in fact, because of quantum effects, quantum confinement, the electrons also can't go all the way to the surface. They actually are just a little bit away from the surface. So the actual oxide thickness for a transistor is higher because of these two effects. And these two, in fact, are bias dependent. So as you change the gate voltage, then polydepletion changes, and also the electron mean position for the electrons also changes. You kind of pull them closer to the surface, even though they don't like to be there. So we see the same thing. If you build a resistor, you also get depletion effects, and so you will see a nonlinear voltage coefficient even for polysilicon resistors. But as you can see here from this table, the numbers are actually quite a bit better. So these are substantially more linear than your reverse bias junctions. Yes?
How about this? Can you explain why VC exists? It seems like they are of same order of almost same number with BC. Is it the same effect occurs for VC?
That's a good question. I don't know the answer. I got this table from the notes. Didn't think about it too much, but I'll double check these numbers with some real processes to see if these numbers are accurate. Good question. Any other questions? Okay, if I forget, remind me to come back to your question. Okay, the other important thing about analog circuits is matching. And the idea is that we're going to build circuits where, let's say we're using feedback. In an open loop circuit, let's say your gain is GM times RL. So you're actually sensitive to the absolute value of resistance. That's a really bad thing because the absolute value of resistance can vary a lot. Depending on the technology, it might be 30–40%. So your gain would vary 30–40%. So really what we do is we try to avoid circuits that rely on absolute value of resistances, right? There's two places where we just don't have a choice. One of them is a band gap. So if you build a band gap, you get a really nice voltage, which is more or less independent of all the resistor values you use to build that band gap. But to turn that into a current, you need a resistor. And if that resistor is on chip, your currents are all going to vary on chip with that resistance in an absolute fashion. So that's one place where we kind of have to bite the bullet. A lot of times people will use an external resistor. Those have one precision external resistor, let's say a 0.1% accuracy resistor, but that's okay because it sets up the bias for the entire chip. So I can live with one external resistor. The other place is time constants. Because time constants are like RC time constants, then as C varies and as R varies, the time constant will vary as their product. And so it's not untypical to see variations on the order of 15% or more. Okay. We should also talk about different kinds of variations in resistances. So here we have systematic variations, run-to-run variations, and then random variations. So let's talk about these three things one by one. Okay, so systematic variation is actually just quite trivial. It's like pretty much you could say it's something under our control. So let's say I build a resistor, and then I need to make contacts to it. So I have, let's say, a piece of polysilicon that's bigger, and then I put my contacts here and here. Now inside this region, once I'm inside here, I know the resistance is roughly L over W times sheet resistance. But over here, right, the current is going to spread out, and there's also contact resistance. The contacts themselves might be 3 to 4 ohms per contact. And so let's say I'm building a 100 ohm resistor. And if I'm just sloppy and I just put down one contact here and don't really take into account the effects of non-uniform current flow here and here, I may end up just systematically getting a mean value instead of 100 ohms, 110 ohms, right? Well, that's my fault. I just didn't do a good job. If I really do need 100 ohms, well, then I shouldn't just use one contact. In fact, I should use a lot of contacts to minimize the contact resistance. It's always a bad idea to use just one contact because that's a good way for your chip to fail. It's very likely that that one contact may not work, and then your resistor's floating. So always use more than one contact. And if I do a good job and take into, make sure that the layout is right, I can really I can take the systematic error away for the most part, right? So that systematic error is not a big deal. Okay, but no matter how good I design this resistor, I get it back. I'm going to get 100 ohms, and it'll probably be a Gaussian distribution, right? There'll be some that are 110, there'll be some that are 102, be 98, 95, right? So I'm going to actually get 100 ohms on average, but there's going to be a sigma. And there's basically two kinds of sigmas that we should worry about. So if this is my wafer, and I'm building resistors, there's one sigma which is the variation from one chip to another within a wafer. So if this is a chip and this is a chip, then they're on different parts of the wafer, and because of the way the doping is done, if you guys are interested, you can talk to your technology friends in this class, it's never going to be uniform. There's going to be pockets where the doping is higher, where the doping is lower. So just if you're just sampling chips randomly and they come from different parts of the die, the resistance is going to vary. Okay, and it's going to vary depending on where you are on the wafer, and it's also going to depend on run to run. So wafer to wafer, there'll be a variation. Okay. Well, luckily, that's really shouldn't be a concern. If you design your circuits right, what you should really be concerned about is variations within the die. In other words, for structures that are close by, physically close together. If you put structures physically close together, variation will be very small. Okay? And so even though you don't know the absolute value of this resistor, it's not going to be 100 ohms, it's going to be maybe 110 ohms, the guy right next to it is not going to vary just as much. It's going to vary probably by 2-3%, depending on how close you are. So that's really a big reason for using resistor ratios, because now we don't depend on absolute values of resistances, but they're ratios. And ratios should track very well. Okay? So let's switch back here. So that's why we're going to use feedback networks, right? Feedback networks naturally give us transfer functions which are inverse of our feedback factor, which is some kind of function of ratios of resistors. The other thing that we're going to do is we're going to carefully place the layout to try to control variations. And let's see, do I have a slide on this? Yeah. So the idea is that, let's say I need to build a resistor. Let's say I need to build a resistor ratio of 1 to 2, as I've shown here. So one way to do it, draw it over here, is basically just put down one resistor like this and put down another resistor like this, right? And basically make these lengths 2 to 1. Okay, why is this a bad way to build resistors? Okay, contacts, right? First of all, you have systematic error. Even if I know the exact resistance of these contacts, and let's say I've taken them into account, well, they both have the same amount of contacts. You don't have twice as many contacts here as you do here. So right away, you're going to get a systematic error due to the contacts. What are some other reasons why this is probably not a good layout? Yes?
You have gradient from left to right.
That's right. So the way to imagine this is picture the doping coming in a particular direction, the dopants. So let's say the dopants are coming in this direction, and let's say that the doping is higher here than here. So this has a lower resistance than this one. So then you're not going to get a 2 to 1 ratio, not just because of the contacts, but because the doping is varied. And the idea is that even though these are very close together, so you make these close, so the doping variation is very small, you still will see some variation. And in fact, if we had been a little bit more clever about the layout, we could avoid that. So again, let's go back to the slide and see how you do that. So what I'm going to do here is I'm going to lay out my device with 3 unit elements. For the moment, let's ignore these dummies. So then I could just connect one like this, right? And then I could have one resistor here. So this would be 2R and this would be R, 2 unit elements. Because I'm using unit elements, I have this double the number of contacts. And so this seems like a really good way to do it, right? So here, I use 3 unit elements. So this is R, this is 2R, and I could just use a piece of aluminum with very low resistance, or copper, depending on the process, and this would give me 2R, and this would give me R. So I've taken care of the systematic variation, but I still have a problem with gradients, right? So if the doping gradients are here, right? Imagine this as like a hill. So let's say the doping is higher here than here, then this is going to have lower resistance than this guy, right? The unit elements. So what could I do to take care of that? Yes.
Yeah, to interleave the resistors.
Yeah, interleaving. So what if I put my unit element R in the middle and then now connect like that? How does that take care of the problem? Well, let's say this is R plus delta R. Because of the same doping variation, let's just call this R, make things simple. Let's say this one is doped a little bit higher, so it's R minus delta R, and this is doped a little bit lower, so it's R plus delta R. Well, you now see that to first order things cancel out because the resistance here is R minus delta R plus delta R plus R. The delta R's go away, and I have a resistance of 2R and R. Okay? And you can convince yourself that this actually is a pretty good idea. It works pretty well. If there's a doping gradient in this direction, it doesn't affect things. It's only a doping gradient in this direction that affects things. And for any gradient, I can decompose it into two gradients, right? And it's only this component that matters. So this layout technique is actually pretty nice. It allows us to design very precise resistor ratios. Okay? Again, let me emphasize that the absolute value of resistance will vary. But at least it will not vary due to systematic errors, and it will not vary for devices that are placed close by. Okay, one last point. Why the dummies, right? Why is it that here I place dummies? Now what am I going to do with these dummies? Where do I connect them? Yes?
Due to etching effects of.
That's right, yeah. So as I said, we have some people in this class with some experience, so don't be intimidated if they're answering all these questions and you're like, how do they know that? Okay, so the idea is that when you're doing unit cell designs, you're going to do an array of devices. And what you want to guarantee is that any particular sub-device sees the same, let's say, environment as much as possible as the rest of the sub-elements. In that way, you guarantee that they're going to be matched as well as possible. So for this guy at the end, there is a big discontinuity. The guy at the end, okay, on one end sees a resistor. On the other end, it sees, let's say, nothing, or maybe some other device that you've placed there. So you've already introduced a systematic error into your design, because the end, you're going to have end effects. In fact, what you're going to do is you're going to find that in fabrication, the guy on the end is actually going to look different because of the way you actually etch these guys. There's etch effects. The space between these may be quite small, and the amount of etchant that gets into these spaces is going to be different than the amount of etchant that gets on the outside. So you're going to get a systematic error. So what you want to do is protect yourself. Just put dummies at the end and don't use the dummies. That's it. Very simple. Okay? Questions? All right, and I think so. Here is a couple of other techniques that you can use to get better resistors. Certainly, if you're going to build a large resistor, you're going to use a layout like this. This is called a serpentine layout or snake-like layout. If you look, I think I put this book on the reserve list. There's a few good books out there that just focus on layout, and I encourage you guys to read these books, especially when you're doing your first tape out. But you can play all sorts of tricks with layout to try to not only get rid of dopant variations, but also process variations. Well, we'll talk about some of that stuff when we look at capacitors and transistors. So let me skip ahead a little bit here. All right, so there is one thing we didn't talk about, and nobody brought it up. Why not use a MOSFET as a resistor, right? It's a transresistor, but if I don't put a signal on the gate, if I just hold it at a constant voltage, then it's a resistor, right? Well, it's nice. It is a resistor. In fact, it's a very useful resistor. We're going to use it as a load in our circuits. You can obtain very high output resistance out of a MOSFET, and so you can actually, for the same voltage headroom, you can get much higher resistance. So let me just talk about that here. Let's say I'm designing an amplifier and I want to get large gain. So I could put a large resistor here, but that's going to consume a voltage headroom of I times R, right? Pretty soon I have to stop. Either I have to stop increasing the current or stop increasing this resistance. And it's going to take a huge layout, right? And in fact, we didn't talk about it too much yet, but with layout always comes capacitance. So this is also potentially going to hurt our 3 dB frequency. We'll talk about this towards the end of the lecture, if I can just speed up a little bit. On the other hand, if I use a MOS device in saturation, then how much headroom do I need to keep it in saturation? VD sat, right? So as long as I maintain VD sat here, this device is in saturation and the resistance I get is RO, which is very nice. So definitely I like to use MOSFETs as loads. If I use it in this configuration, it's acting like a current source, but I can also use it in triode region, right? So instead of biasing it, I can put this thing in triode region and again use it as a resistor. If we look at the IV curve, look something like this. Effectively what you're doing is you're picking a certain value of V gate, call that VC, and as you vary VDS, then you can see that the resistance is going to vary, right? And you can see that it has some curvature to it, so it's not a very good resistor. In fact, if you use it over here, it's the most linear region, and the closer you go, higher you put the voltage across it, the more nonlinear it looks, right? So there's some restrictions over the voltage swing you can put across it and its linearity, but it's actually a pretty decent resistor. It's not a very precise resistor, though. So it has the same problems as the other resistors. In fact, the variation might be even more. And it's also quite a nonlinear resistor. So here, very simple calculation. If we assume even square law, which is in fact somewhat generous, then if we calculate the change in the current as we change the VDS across the device, very simple, pops out, that gives us the resistance. But unfortunately, if now you take the derivative of the resistance with respect to VDS, you will find that actually it varies quite a bit. So the voltage coefficient is 1 over VGST minus the actual VDS on the device. Now, in reality, here we assume the mobility is constant as we change VD and VG. In reality, the mobility also changes as we change the drain voltage. So this is really an oversimplification. Okay, well, one nice application for these guys is a very, very large resistance. Let's say you need a mega ohm, or even let's say a giga ohm of resistance, right? Almost inconceivable to get a giga ohm, because just leakage currents would probably be lower resistance than that. But in some applications, if you have the right environment, you can even get a giga ohm, as seen in this paper here. Really, this is a great application for these MOSFETs. Let's say you need a large resistance. The exact value is not important. It just needs to be large enough. Let's say you're biasing up a transistor and you want to isolate the bias circuit, so you use a large resistor. It needs to be a mega ohm or more. Okay, this is a good application for using MOSFETs as resistors. Okay, so this is a quick summary of what we've learned about resistors. In some ways, they're very costly. Now, chip area is expensive. If a resistor needs to be physically large, it's going to be expensive. It has non-idealities. It has voltage coefficient, temperature coefficient, and it also has process variation. And so what we've learned is good layout. With good layout, we can minimize the process variation for ratios of resistors, although the absolute value will still vary. And so what it means is that really we should avoid using resistors if at all possible. If we have circuits that work just as well without them, hey, get rid of them. No reason to keep them around, okay? Any questions about resistors? All right, so let's talk about capacitors. Now, capacitors are also ubiquitous in integrated circuits. Large value capacitors are needed all over the place as bypass capacitors. You can think of them as your local battery inside the chip that's close to the circuit that's drawing the current, right? The further away you are from your source, the more inductance and resistance there is, and therefore the more supply bounce that you get. So in order to mitigate supply bounce issues, you have to have a capacitor nearby as a reservoir of energy. Okay? In fact, this not only applies to integrated circuits, it also applies to power, like the power we get, the lights coming in. Anybody ever seen a bypass capacitor for power applications? They're big, right? They're physically, bigger than we are. But if you drive by and you see like a cage with all these cylinders and wires coming in and out, that's like a bypass cap array. You put them outside like a factory that has lots of, let's say you have a factory with lots of motors, lots of inductance there. So if you don't have that capacitor, the angle of your load is actually going to be really bad for the power supply company. They have to supply inductive power to you, and they're going to lose money. So they actually will require you to put a bypass cap on site to compensate for your load angle. We need them on chip too. If we don't have bypass capacitors on chip, the supply voltage will vary so much that it'll start eating into our margins, even for digital applications. Okay. We also need large values for compensation. So if we build amplifiers and we want to have low frequency poles, we need large capacitors. And we know some tricks to get around that. For instance, we know Miller multiplication helps. But in some applications, you can't Miller multiply. You just have to use a capacitor to ground. And so you need large values of capacitors. You also, again, would like, so for large values, accuracy is not an issue, just large enough. But there are applications where you do need accuracy. And we're going to see that filters, for instance, obviously filters are made of R's and C's or L's and C's. So if you want accurate corner frequencies, you need to have accurate capacitance values. And also, increasingly, in CMOS analog circuits, we're going to use capacitors as feedback elements. And again, ratios of capacitors become important. So here is, in a typical CMOS process, what we have available to us, right? Anything you put on top of the substrate is a capacitor. The question is it a good one or is it a bad one? Well, good in this sense would be density. The more dense the capacitor is, the better, because that way I can make it smaller. Doesn't cost me as much, but also the smaller I can make my capacitor, the less substrate parasitics it'll have. The substrate parasitics, sometimes called the backplate parasitics, are an issue. So for instance, let's say I build a poly capacitor. Let's say it's a poly-poly capacitor. So I have a polysilicon, an insulator, polysilicon, and so I have my actual capacitance that I want, that's between these terminals, but I also have this backplate capacitance, which is a parasitic, right? The front gate is shielded, so it doesn't, you get a little bit of fringing fields from the front gate, but mostly it's the back gate that sees the substrate. Okay, so the higher the density I can make this capacitor, the thinner I make this oxide, the less this matters, because I can physically make it smaller. Okay. So coming here, back to our slide, we see that we have several options available to us. For instance, gate capacitance, right? MOS is a great device. You could use it a big resistor. You can also make a big capacitor because the oxide is so thin. So I can use my MOS device in inversion or in accumulation and get very large capacitance. Here's a typical value. It's actually larger than that for our process. But again, thousands of attofarads per micron squared. The problem, of course, is the voltage coefficient. It has a huge voltage coefficient, right? Remember, the CV curve of a MOS device looks like this. So if I bias my device here, and this transition is very fast. So this is inversion, right? And then this is depletion. So the transition from depletion to inversion is exponential. So this is actually a very steep curve. And so this transition, so this is from basically depletion to inversion. And so right like a couple hundred millivolts around VT, we see this transition occurring. And that means our capacitance varies from Cox to Cox in series with C depletion. And so this could be a 3-to-1 variation, 4-to-1 variation very easily. That means this is very steep. So our voltage coefficient is very bad. Okay, back to the list. Okay, poly capacitors, they also don't have quite the same density, but they come close. But they are usually an option. They don't come standard. And again, we get the polysilicon depletion, which gives us a voltage coefficient.
Question.
Yes.
Why the temperature variation for the gate capacitance is big, and how big it is?
Yeah, it's because of VT variations. The threshold voltage varies with temperature. And we'll talk about that more next lecture. VT varies, right? Your capacitance varies enormously. It's a good question. Okay, metal capacitors, why do they have a voltage coefficient? I don't know, actually. It seems like if you build metal insulator metal, it should be pretty damn linear, right? Maybe this is a typo. Maybe you're using a weird insulator, and that would give you a problem. So if you're using an insulator with a very high epsilon value, right, not native oxide, then there could be some nonlinear effects, right? You could have dipole moments that change direction as you change the field, and basically, if you're fighting, let's say KT energy on those dipole moments, then the higher the field, the more capacitive energy, the more dipoles you're likely to align. So it would give you a voltage coefficient. But otherwise, I don't know why it would be there. You also have some parasitic capacitors that you probably don't want to use. Just any metal that you put on top of the substrate, right, will have parasitic capacitance to the substrate. And the higher you go up the metals, the lower that parasitic is, but it's still there, and you have to live with it. In fact, the polysilicon layer has the highest parasitic capacitance. If we draw a cross-section of a typical process, so we have our substrate, then we have our poly. This is our gate poly. It's very close to the substrate. That's why it has a high parasitic. And then you have basically metal layers, and they just do what they do. They're capacitors to substrate. So this is one plate, and this is another plate. So you have capacitances between layers that you can use, and you have capacitances from layers to substrate that you can use. Now, if you're going to use the substrate, you better put a plate there. So I would, if this is P substrate, and let's say this is an N well for isolation, then I would put N plus here to form the other terminal of my capacitor. Otherwise, it's capacitance to ground, and a very lossy ground for that matter. Okay. And going back to our list, of course, if we can build a PN junction, we also have a capacitor. So these are the options available to us. They all make sense in certain applications, and they all, so it's really, there's no magic bullet, but increasingly nowadays in a modern CMOS process, you have custom MIM capacitors, actually high density metal insulator metal capacitors available to you, and you can use them, and they're very linear and they have very good performance, and we'll look at some numbers a little bit later. So what I'm going to say here, it applies pretty generally. Let's just go through a little bit. So here's a MOS capacitor. So if you want to simulate a MOS capacitor in SPICE, here's a very simple way to do it. One way is to actually access the device parameters, right? You can go in and plot the CGS of the device, C gate to drain, C gate to body, add them all up, and that's your total capacitance. Another way to do it is you just run an AC simulation, and in this simple AC simulation, you can see that the capacitance just works out to be the current going into this source, right? You can verify that. It's very simple. And so I can now measure the capacitance as I vary VGS and possibly VBS and see how much that capacitance varies. And this is the result for our class transistor. Just to make sure that the simulation works, I put down a known capacitance of 200 femtofarads, and then I ran the simulation. This is always a good idea. I'll recommend this in general. Whenever you run a simulation, I call it run a sanity check first, because you can make so many mistakes. You can forget factors of pi. You might be interpreting the simulator wrong. So always put down something known, plot it. Okay, I know that this curve here should be 200 femtoamps, right? Because amps are farads here. And yes, it does hold, so my calculations were correct. And then I plot the same thing, the current going into my capacitor, and you can see that, again, this huge variation from this point to this point. You can see the capacitance changes almost 3 to 1. This is, again, that exponential increase in charge, which leads to this great change in capacitance. Over here, it's more gradual because of the depletion effect, right? So this part of the curve is much more gradual than this part of the curve. If you look very carefully, you'll see that this curve actually is going downwards, right? In fact, the capacitance is decreasing as we increase the voltage, right? You would expect that these two curves on the left side and the right side should line up, and they actually almost do, but they're slightly different, and that's because of what we talked about earlier. Over here you have polysilicon depletion, and you have quantum effects. Polysilicon depletion would actually make these curves go downwards. Quantum effects, probably for such a small change in voltage, you wouldn't see much. And what you would see instead is that this curve would not go quite as high as this curve, because the electron position relative to the surface would be different from the holes. So the quantum confinement would be different. Another thing to notice here is that the capacitance varies quite a bit with process. So in the model that you have available for this course has process corners. And so SS would be a slow process. A TT would be a typical process. And FF would be fast. Okay? And so the notation is that typical is like your average transistor, right? And your fast transistor and your slow transistor are kind of your, let's say, 6 sigma or 5 sigma, or whatever the process is specified. Those are the most extreme transistors that you would expect to get. And the traditional way of doing analog design, and also digital design, circuit design in general, has been make sure your circuit works for all process corners. Now, process corners in some ways are very artificial. You're never going to get a transistor that falls exactly within the corner. But the idea is that if your circuit works across all the process corners, then very likely, on average, it'll work. Okay? Now, that way of design will probably change in the next few years. You guys will probably witness that change because it's just way too pessimistic to try to make your circuit work at all these process corners. It's much better to do statistical design. In other words, if you have a transistor model that's physical, then I can physically vary the parameters of that model, let's say the channel length, channel width, the oxide thickness, the mobility, the temperature, whatever I know that's varying, and then I can do some Monte Carlo simulations. So in fact, I can run some Monte Carlo simulations and see what the yield of the circuit is going to be. If the yield is high enough, say it's 98%, great, ship it. And it may not satisfy the process corners. So that's something that is historical, and if you go out and work today, you will be working with process corners. It's very common, but something that I think is going to change in the next few years. So one of the first things you should think about in this course, you probably haven't thought of before, is anytime you do a design, don't just simulate it at typical corner. Simulate it at slow, simulate it fast, simulate it at hot, simulate it at cold. Change the temperature, change the process. PVT, process and temperature variations. Okay, polycapacitors we already talked about. We talked about the bottom plate parasitics and the shielding, so I'll just skip ahead a little bit here. Here's a nice little layout from Savidis' book, Mixed mixed signal analog digital VLSI design and technology. This one I don't believe is on reference, but it is at the library. So here is just showing you this idea of doing, again, a unit cell capacitor design. And spend some time and look at this picture. It's actually pretty neat. What you see here is that you've designed unit cells that either connect to their neighbors or don't necessarily connect, right? So by having these staggered, I can either make a connection or I don't have to make a connection. And the reason I do that is that I want to do a unit cell design where I have this capacitor and this capacitor, and I want their ratios to come out very accurately. I want to get rid of systematic errors. So if I don't have these little, let's say, stubs on this guy, which doesn't need to connect, then I would get a systematic error. But here, by having this stub, I can either connect it or not connect it, and I'll get an extra capacitance due to that stub, but that's part of the design. So it's a very nice way of doing the layout. Again, it's very similar to the resistor we talked about, but here, because in the resistor, the interconnection just added a little bit of resistance, and it was aluminum, and it was an order of magnitude less sheet resistance. Here, if we add these little stubs to interconnect, they're going to add capacitance. And, you know, in this particular example, you can see the capacitance of this interconnect is a good fraction of the total capacitance. And it's going to fringe, so it actually is going to look even wider than it looks physically. So definitely I want to include that in the systematic layout of my capacitor. And then finally, you see that dummies are used all around as well. So these are the dummies. If you're really, really careful and wanted to make sure that the design was as systematically close as possible, then probably you would make your dummies out of the unit cells as well. Okay. Any questions about this picture? Yes.
What's that ring surrounding the whole structure?
The ring around it, that's the shield. So again, this is a poly-poly capacitor, and there's a back plate. And if I don't put anything down, then this will just go to substrate, right? But what I can do is I can actually put a diffusion here. Let's say this is a P substrate. I can put a P plus and ground this point. And so now I have a very well-defined place where my backplate parasitic is grounded. So in circuits, especially circuits that depend on charge, I want to make sure I do good accounting of charge. I want to know where my charges are going. And this is a good way to capture the fringing fields and terminate them at a known point. Okay?
Question?
Yes.
Is the body the same as a gate? The poly as the same as a gate poly, or just different?
One of the layers is the same as the gate, and then there's a second poly layer in this particular example. Now,
so the back gate capacitance is going to be very huge, right? Because it's gate.
Yeah. Exactly. Yeah. Nowadays, actually, most processes have an option of giving you a high-quality capacitor. So, in particular, we'll look at a process that gives you a MIM capacitor, not even poly, MIM, which is even better in the sense that the gate resistance is, the plate resistance is going to be much lower. And those are not sitting right on top of the substrate. In fact, they're up at really high metal layers, so they have very low backplate parasitics. Okay. Very quickly, let's look at these metal capacitors. In fact, I forgot I had a slide on it. So it's an add-in option. So basically, you don't get them for free; you pay for them. But they give you good density and the low backplate parasitics. And then finally, I just want to say that sometimes you can get something for free, and these are the so-called MOM capacitors, or metal oxide metal capacitors. And the idea is that lateral dimensions in a modern CMOS process are very, very small. You can put metal layers on the order of 0.1 microns away from each other, right? So that means that I can get very large lateral capacitance. So this is exactly what's shown here. These are finger capacitors, another name for them. It's basically like a comb structure that gives you very high capacitance between the fingers. And because I have so many metal layers available to me, in a typical process, I might have 8 metal layers. I can stack 8 metal layers on top of each other and get very high density capacitors. So here's a picture of what it looks like in cross-section. you can see that I'm getting capacitance not just from the metal layers, but also from the vias. So I want to connect these all together and get a very high capacitance. And the amount of backplate parasitics is also controllable. I can drop metal layers here and reduce the backplate capacitance, thereby increase my distance to the substrate. Okay. Any questions about MOM capacitors? Okay, we'll pick it up the next lecture.